This conference will now be recorded.
Good morning, ladies and gentlemen. This is Ben Keyser with Applied Flow Technology. I hope that you all are doing very well and having a wonderful week. And want to thank you for joining in on our webinar today as we discuss how to size your pipes to meet different operating cases. Before we get into that, really quick, I just want to highlight a couple of things. First off, if you go to our website, aft.com, under the products menu, you can find our software overview, which is where you can learn high-level details about our different software tools, AFT Fathom, AFT Arrow, and AFT Impulse. And as you can see, each product has a number of add-on modules that can be used with it. And today for AFT Fathom, I'm going to be demonstrating the automated network sizing module. Now, as you can see, AFT Arrow also has a automated network sizing module. Therefore, the process of using the ANS module in Fathom is the same as it would be able to be used in AFT Arrow. So if you are using Fathom for liquids or Arrow with gases, the process I'll be demonstrating is exactly the same. And so when you learn one, you know how to use the others. If you go to the AFT Fathom page itself and scroll down to the bottom, this is where you can find the add-on modules. And if you click on the automated network sizing module itself, this is where you'll be able to learn more about what this module does and how it can help you with your design processes. In short, the automated network sizing module is going to help you automatically meet your design requirements by sizing all of the pipes for you in order to minimize either your monetary cost of your piping system or the piping weight, because maybe you don't have cost information. If you are minimizing your overall piping weight, that tends to track really well with minimizing your initial costs. So this webpage will give you a lot more information about that. Second thing I wanted to highlight is that I am going to be demonstrating a model today that I did a previous webinar on a while ago. And so if you were to go to our Learning Center and then Webinars and Webinar Library, here you would be able to fill out the form, and this is where you can access all of our previously recorded webinars that are available to you on demand. So once you get into our webinar library, you can go into the AFT Fathom webinars, and in the AFT Fathom webinars, if you scroll down a bit, there's a webinar called Size Your Pipes in No Time Flat. In that particular webinar, I go into really good detail on how you would be able to size a piping network if you do not have any cost information. So that's where you are minimizing the overall piping weight of your system. And I'm going to be demonstrating the same system today that I did in that previous webinar, but I'm going to take it a step further and advance it up. And so if you want to be able to have a more step-by-step guidance on how I sized the pipes in this system, then you can refer back to this webinar, because I will cover it today, but I'm going to be going through that stuff fairly quickly. So if you want to be able to watch that part of the webinar again, be sure to watch Size Your Pipes in No Time Flat. Now, a little bit of background where the system that I'll be demonstrating for you today came from. In near the end of 2018, a couple years ago, I did a 2-week road trip through the South, where I had the opportunity to do, I met with a lot of consulting companies and chemical plants and oil refineries. And there's one particular oil refinery that I was doing a lunch and learn for. And one of the senior managers came over to me and told me that they recently, at that time, were just putting in 2 new heat exchangers into service. And he told me that he asked upper management if they decided to, or if they did a flow analysis to make sure that things were going to work. Well, he said that upper management actually said they decided not to do a flow analysis. Not just we didn't do one, we decided not to do one. Sure enough, when they were ready to commission the system and they turned on the two new heat exchangers, they didn't get any flow at all, and the pumps were already maxed out, serving everything else in the system. So that was a really good case study to me on how important it is to take the time to actually do a flow analysis. And so I wrote an article for the Pumps and Systems magazine back in February 2019 about that. And so if you go to Pumps and Systems magazine in February 2019's magazine, this is the article that I wrote where I essentially told that story. So basically, there's this system that was initially operating, and later on, they wanted to add in this expansion loop. And this is the article that I wrote on why it's really important to do a flow analysis, because if you're going to throw in an expansion loop, then it's a really good idea to ensure that it's actually going to work and give you what you need. So that's where the system that I'm demonstrating for you today came from. So if you read that article, it'll give you a little bit more background about that. Okay, so now I'm going to go ahead and jump into AFT Fathom, and we're going to go ahead and get started. So in that particular article that I wrote, the story was such that this part of the system was already fully designed, fully sized, and was completely operational. And later on, we were going to be sizing the pipes for this expansion loop. However, in this particular situation, I already know if I'm originally designing this entire system, including the expansion loop, it's a really good idea when you're sizing your main operating system to perhaps account for a expansion loop at the beginning of your design process. The reason why is because even if you don't know exactly what your design requirements might be for your expansion loop, if you know that you might want to be getting some more flow to another part of the system later down the road, it might be a really good idea to size your existing pipes such as well as your pumps such that they can accommodate higher flows in another part of the system later on. That's the advantage to using the automated network sizing module, is because it makes it really, really easy to size your system and pre-plan a expansion loop to your design ahead of time. That way everything is sized a lot more efficiently from the very beginning of your process. So what I'm going to do is I'm going to start off with how you would go about sizing this entire system from the very beginning. And as we can see, I have one design case where through each set of heat exchangers here, I want 1400 gallons per minute each. And then in my expansion loop, I need 1300 gallons per minute each through each heat exchanger. And so I'm going to size the pipes in my entire system as well as the pumps to accommodate those flows. So my system is fully built and I have a green status light and all of the checklist items are completed. And so I can run my model and I can get results and see what's going on. But none of these results matter to me because it's not real data in terms of the pipe sizes. If you notice, I'm using a starting pipe size of 16 inches in diameter for all of the pipes in my system. That is just a guess. It's only a starting point, and I'm going to allow the automated network sizing module to size the pipes for me. So I know that the majority of the time, this entire piping system is going to be operating for these particular flow rates. Later on in this webinar, I'm going to demonstrate where we have a second operating case where maybe we need to accommodate the system with more flow. And so in design case number 2 that you'll see shortly, we want to design our system to accommodate 35% more flow all throughout the network. And this is going to demonstrate how you can actually size the piping system for both cases. It's going to size your pipes to accommodate the normal operating flow of these values, and then I'll show you how it can size the high flow case as well at the same time. Now, in order to do that second case, we have to set up all of our automated sizing parameters for this part of the system initially. So I'm going to go ahead and walk through that. Again, I'm going to go quickly, so just bear with me. If you want to be able to see the webinar that walks you through a bit more step by step, be sure again to refer to this webinar, Size Your Pipes in No Time Flat. Give me 1 second. Okay, so to get started, what I'm going to do is I'm going to create a scenario. I'm going to call this automated sizing for one case. All right, so in this scenario, I'm going to turn on the automated network sizing module, and here's a nice handy dandy button that allows you to turn on the add-on modules, and I'm going to check the box for ANS, and that gives me access, and we'll click OK. Try it again. There we go. All right, so now you can see that I have a new checklist item to define all sizing input and a red status light. So that just means that now that I've turned on the automated sizing module, this is a new sizing panel where I have stuff to do in order to allow my pipes to be automatically sized for me. So that's where all the magic happens. So I'm going to go to the sizing panel, and I'm not going to walk you through what all these different options do. I've already covered that in previous webinars. And so what I'm going to do is I'm just going to stick with the defaults to perform a pipe sizing of my entire system. I don't have any monetary cost information for material, installation, maintenance, energy costs. I don't have any of that. So I'm going to size my pipes based upon the overall piping weight, and my goal is to actually minimize that piping weight. Again, if you minimize your piping weight, that will track really well with minimizing your overall initial cost. And if you enter in a design requirement for a maximum velocity, that also will kind of help balance things out to try and help reduce the energy costs in the long run as well. So keep that in mind. All right, the first panel for the sizing objective is already completed. The next step is to do my sizing assignments. So this is where I pick which particular pipes I want to size. Well, in this system, I'm going to size all of them. I have 35 pipes that I need to size. So when I go back to the sizing panel here, what I'm going to do is I'm going to click on the All button, and that is going to select all of the pipe rows for me. And then I'm going to choose this option to always include in weight. If you were doing a monetary cost sizing process, it would say always include in cost. And this will allow your pipe sizes to be changed for you. Now, as you can see here, we have 35 independent pipe sizes. What that means is if I go back to my workspace and I don't make any changes, then this could mean that I might be using 35 different pipe sizes throughout my entire system. That could result in a very good design that really minimizes that piping weight. However, it's going to drive your purchasing department insane. So you want to enforce maybe some level of commonality through various flow paths. So as an example, maybe in this particular flow path here, I want to have the same pipe size. So that's what we call a common size group. So if I want to size all of these pipes right here and change them such that they all end up having the same diameter, that's what we call a common size group. So when I go back to the sizing panel here, I'm going to create several common size groups. So I'm going to click on new and give it a name. I'll start off with main header, and I'm going to create several more. Pump A pipes, pump B pipes, pump C pipes, heat exchanger A pipes, heat exchanger B pipes, heat exchanger C pipes, and heat exchanger D pipes. There we go. So I have 8 common size groups that are going to be in this particular model. Now what you need to do is you need to select which specific pipes are going into a particular common size group. Now this is really easy to do. So I'm going to collapse my quick access panel so I have a little bit more real estate. And if you have a second monitor, you can move your sizing panel over to another monitor and it makes it really easy. But since you can't see that for the webinar, I'm going to dock it to the right hand side and then I'm going to resize the workspace. All right, so here's how we do this. I'm going to start selecting various pipes on the workspace and I'm going to add them to different common size groups. So here's how you do it. I'm going to click and drag from right to left to select those pipes, hold the control key down and select these pipes as well. And those selected pipes are going to be my main header common size group. Once you select them on the workspace, click the workspace button and that selects the rows for you. Once these are selected, you can go to click on move to, and this is going to be main header. And then you would simply go through and do the same process to add various pipes to your other common size groups. So you just select them on the workspace, click on the workspace button, and that will select the rows, and then you click on move to and you just pick which common size group they're going to belong to. So those are my heat exchanger A pipes, workspace, move to heat exchanger B, and then select workspace, heat exchanger C, and last but not least, select workspace, heat exchanger D. All right, so now I'm going to reset my panes and we can see that all of our pipes are added to various common size groups, but this is not sorted the most conveniently. It's sorting everything by the numerical pipe number order. Well, if you just click on the field right here where it says common size groups, that will automatically filter and sort everything by common size group. That way you can easily see which pipes go with which common size group. Now, as you can see, these pipes down here do not belong to a group. That's perfectly fine. They could potentially have different sizes or they might be the same. It just depends on the math. So I just went from 35 independent pipe sizes down to 14. Less variables means less equations need to be solved, and that way my runtime will be a little bit faster. All right, so now that I've got my pipes all added to their various common size groups, next step is to go to my candidate sets. I'm going to pick a pipe material with various sizes that are allowed to be used for this particular system. So the first thing that you would do is you're going to click on New to create a new candidate set. I'm going to call it steel 1-inch to 36-inch standard schedule. Now you would choose which particular material you're going to use. So this is going to be steel, and I'm going to use my standard schedule pipe sizes. You could do other schedules if you want, but I'm only going to use standard. So if you click on the schedule level and click add, it's going to add all the sizes in that schedule for you. Makes it nice and easy. But I'm going to delete the sizes that are smaller than 1 inch in diameter, and I'm going to delete the sizes that are larger than 36-inch in diameter. Now you can do multiple candidate sets. So maybe some pipes can be steel, other pipes might be HDPE or copper, etc. That way you can apply different candidate sets to different common size groups. But here in my model, everything is going to be using steel in this particular case, just to keep it simple. So I'm going to click all, and then I'm going to assign all of these common size groups and the pipes that are not in a group to use steel 1 inches in diameter. So that step is pretty easy. The last step here is to specify my design requirements. So this is really important because this is what's going to drive your pipe size design. So the first thing I'm going to do is I'm going to create design requirements for my pipes. So we're going to click on new, and then you give it a name. So one of the design requirements is that all the pipes have to have a velocity that's less than 10 feet per second. So I'm going to call it 10 feet per second max velocity. Then you choose a parameter, which is going to be velocity. Whether it's a maximum or a minimum value, this is a maximum of 10 feet per second. So that's my first design requirement. Second design requirement, I'm going to call this 1400 GPM HX A and B flow. This is going to be based upon volumetric flow rate. Minimum is going to be 1400 gallons per minute. And now that I have this set up here, I'm going to select that row and I'm going to duplicate it and give the second one a new name, 1300 gallons per minute heat exchanger C and D flow. And all I need to do here is just change the number. So when you duplicate a row, if you have very similar design requirements, it can save you a little bit of time. Now that we have created some design requirements, we need to pick which common size groups the design requirements are going to apply to. So here, if you expand any of these common size groups, you can see which pipes belong to that common size group. The 10 feet velocity applies to all common size groups. So I'm going to check the boxes for all of these common size groups. And when we expand it, if you check the box on the top level, it will check the boxes for all of them. So you can see how this will save you some clicks when you toggle things on and off. Next, we need to apply our other flow design requirements to the various heat exchanger flow paths. So the first one, 1400 gallons per minute, is going to apply to my heat exchanger A pipes and heat exchanger B pipes, and then 1300 is going to be for C and D. Now let's go back to the workspace really quick here and dive into things just a little bit deeper. I have this control valve set to 1400 gallons per minute, and then my other control valve is set to 1300 gallons per minute. And so that's going to fix the flow through each of those flow paths. Now, this particular control valve also needs to have a flow of 1400 gallons per minute, as would this one, 1300. So I have 1400 through each of these, 1300 through each of these. And the way that I'm sizing my system is I also need to size my pumps. I don't have any pump curves. So the way that I'm sizing my pumps is by using a sizing option with a fixed flow rate of 2,000 gallons per minute. So I have 2,000 gallons per minute for each of these pumps, as you can see. Now, if I was to run my model like this as it is, where I have fixed flow pumps, and then I have a specified flow on each of these heat exchangers, my model is not going to run. The reason why is because in a very basic sense, I have an internal part of my system that is bounded by known flow rates. So you can calculate a pressure drop that will satisfy that flow, but what's the pressure at the inlet of the pipe, or the middle of the pipe, or the end of the pipe? You don't know, because there are multiple solutions that can exist which will give you this pressure drop to satisfy the specified flow. That's where you'll see a reference pressure message where the model is not going to be able to run. So I don't want to go into much more detail on that. I want to click on the help menu, and I want to show you where you can find an example that will give you more detail on that. So if you go to the help menu and then show examples and pick your desired units, there's a example in here where if you expand, it's called pump sizing and selection with flow control valves. So this is that exact concept, but at a very simple level where you have a pump sizing process you need to do. So you start with a fixed flow rate here, and then you have two control valves with fixed flow rates each in parallel. Well, that's not going to run either. So this example here, it walks you through what you would need to do in order to be able to actually size your pump in that situation. Well, you would change one of the control valves to maybe a constant pressure drop, and that way you can get around that reference pressure issue. And so this example will walk you through that process and what it means. So in order to get my system to run, I have to specify these two control valves that seem to be hydraulically more remote to a different model. So I'm going to use a constant pressure drop of 10 psi. 10 psi is actually a design requirement for the minimum pressure drop that I need to achieve across all my control valves, such that they can maintain good controllability for their system life. So I have a fixed flow on this control valve and a fixed flow on this one. I'm sorry, a constant pressure drop. And then we have a fixed flow here and a constant pressure drop here. So now you can see when I go back to my sizing panel, when I set my design requirements, it's going to change the pipe sizes so that I at least have the minimum flow rate that I need through each path. Now, you guessed it. What's going to happen is I'm going to have exactly the flow I need in one path and then perhaps more flow in the other path. Same thing here, exactly 1300 and then perhaps more flow here. That's just the nature of what's going on in our sizing process. So on my control valves tab, I'm going to add a new design requirement for my control valves, 10 psi minimum DP. And this way, it'll make sure that my control valves take out at least a minimum of 10 psi. Now, these are only going to apply to the control valves that are actually specified as fixed flows, because the other two control valves, they're already set with the minimum DP, so that's no issue there. All right, everything is all set up, and the last thing to do is to go to my sizing method, and there are different mathematical options for sizing your system that you can work with. I'm going to use discrete sizing, because the discrete sizing option is going to force a specific nominal size from your candidate set list. You don't want to end up with a size of 3.73 inches in diameter, because you're not going to be able to find that anywhere. So you need to go with standard sizes from your candidate set. That's why we use the discrete option. And so now what I'm going to do is I'm going to check the box here to start with the continuous method. The reason why I'm doing that is because it will start off with using 16 inches in diameter as my first guess. Figure out if the design requirements are met and is feasible or not, and then it'll do a continuous sizing, which is any hydraulic diameter that can maybe get me a better guess than 16 inches in diameter. So now that everything's all set up, I'm going to go ahead and run the model, and it's going to begin the sizing process. So let's break it down. First, it ran the model based upon 16 inches in diameter, and it found that the initial design was infeasible. That's because I had some design requirements that were violated. Maybe the flows were not high enough, or maybe my velocities were too high, etc. And it calculated a piping weight based upon 16 inches of diameter. After that, it starts the continuous sizing process, where it's trying to find the lowest piping weight based upon continuous sizes. Again, that's any hydraulic diameter, to try and get a better guess. Now that it has a better guess for 216,000 pounds, now it's doing the discrete sizing process, where it's trying to find a real nominal pipe size of my standard schedules of steel that will meet all my design requirements. And so right now, the best feasible cost is just under 241,000 pounds, and it finally converged within about a minute and 15 seconds. So that's not too bad. So let's take a look and see what we've got going on. So I can go to my output window, and I'm going to make my size a little bit larger. Let's take a look at the cost report. That's an important place to start. The cost report tells us how much it costs. Well, this is in terms of piping weight. So my total piping weight is 241,000 pounds. Now, this is just an approximation, because it's not accounting for the weight of any of our fittings, like elbows or T's or anything like that, or pumps. So this is just giving you a quick, rough estimate of what your sizes should be, based upon trying to make your piping weight as low as you can. If you want a more accurate sizing of your system, then that's where it's better to do a monetary cost sizing example. Well, we have webinars on that as well. If you go back to our website and scroll down, that's where you can watch the other webinar called How to Utilize the Automated Network Sizing Module. So if you watch this particular webinar, it will demonstrate doing a monetary cost sizing example, and that way you'll have a more accurate sizing of your system. But this does a really, really good job when you don't have any cost information. We can see where our pumps are operating, 2,000 gallons per minute. We need 120 feet ahead. There we go. Here is our sizing results. So as you can see, we are sizing our system on a range of about 8 inches in diameter to about 18 inches in diameter. So that's our range of sizes that we're going with, 8 inches to 18 inches. If I go to my visual report, some of these labels are skewed and strewn about. And so I'm going to show my size, nominal pipe size. And there you have it. So we've got 18 inch, 10 inch, 10 inch, 14 inch on this, 10 inch here. We've got 10 inch pipe size, 14 inches in diameter. Our main header is 18 inches, so on and so forth. And so this is our entire system that is sized based upon one operating design case. That design case is 1,400 gallons per minute through each heat exchanger and 1,300 gallons per minute through the C and D heat exchangers. Now, if I go back to my output table, I can see that all my design requirements are met. So this would work really well if this is exactly how my system is going to run 24/7, 365. Now we get to the meat of what today's webinar is going to be about. This is where we're going to take it a step up a notch. So here we have a situation where we want more flow. So let's say that 60 to 70% of the time, these are the flow rates that we're operating at. But 30 to 40% of the time, we want increased capacity. So let's say that we want to be able to design our system to accommodate 35% increased capacity over what we need here, just in case we have higher production in the future that we need to be able to accommodate. Give me 1 second. Excuse me. So when we go to size our entire system, we want to make sure that we can have pipe sizes that can accommodate higher flow, as well as pumps that can accommodate higher flow. So this is where we are going to talk about dependent design cases. If you were to continue watching the Size Your Pipes in No Time Flat webinar, what I would do there is I would demonstrate how you go about taking the resulting pipe sizes and you convert them into input for your workspace, and then you would size your pumps accordingly based upon your selected pipe sizes. But now what I'm going to do is I'm going to create another scenario here, and I'm going to call it dependent design cases. All right. So now we have a situation where we need to be able to accommodate higher flow, 35% more. So how do you do this? Well, what you do is you go back to the sizing panel, and this is where you would check the box here for multiple operating cases. You can do as many operating cases as you want. I'm only going to do 2 operating cases. So I'm going to check the box, and when you check that box, it creates another item in the panel of additional steps that you would need to do. So if you click on the check mark, or I'm sorry, the question mark, it'll give you some information about what dependent design cases means. So we've turned that feature on. Now let's go back and let's look at dependent design cases. So let me zoom in a little bit here. So when you go to the dependent design cases tab, this gives you a series of steps that you would need to accomplish in order to size your system based upon 2 completely separate operating scenarios. So the first step is to create and fully define your base system Configure the sizing parameters for the base operating requirements. We've already done that. We've already built and defined our system. We've set up all of our common size groups. We've set up our candidate sets. We've defined our design requirements. So all that's done. The second thing is to go to the workspace and select the desired dependent design case system. That's what you see on the workspace right now. Step 3 is to go to the edit menu and click on duplicate special, and that's where you would check the box to say dependent design case. So here's what we've got. I've got my entire system on the workspace, and I'm going to zoom out. If you click all, or Control A, that selects all of your pipes and junctions on the workspace. So now I'm going to click on Edit, and I'm going to click on Duplicate Special. So the first thing it said is to set a increment value. So I'm going to choose 1,000. This way you can see that pipe 1 corresponds with pipe 1,001. Pipe 2 corresponds with pipe 1,002. And then we need to check this box right here to make a dependent design case. So when I click on that option and click OK, I can now use the paste preview mode to move my system around. I'm going to put it right there. And I'm going to paste it to the workspace. And I'm going to collapse my quick access panel. And there we go. So now I have two systems. This system represents design case number 1. This system represents design case number 2. And so design case number 2 has higher flow. So I'm going to change my annotations just to make that clear. So this is design case number 2, and that flow rate is going to be 1,890 gallons per minute through each heat exchanger. And this expansion loop is going to go from 1,300 to 1,755 gallons per minute. So now I have system 1 and system 2 in place. Now here's the beautiful thing about this is when I did that duplicate special, it took all of those common size groups and candidate sets that I already specified in the previous scenario, and it applied it to this system on the workspace. So that way it saved me a lot of time. I don't have to recreate the common size groups or candidate sets for that system. It's already done. But what I do need to do is I need to change my flow demands. So when I go to this control valve here, this needs to be 1890. This is still going to be 10 psi at the minimum pressure drop. And then this control valve here is going to be 1755. Now, originally, the pumps were going to be sized based upon 2,000 gallons per minute, but now I need more flow. So we have 1890 times 2 plus 1755 times 2. So we need an entire flow in our system of 7,290 gallons per minute. If we take that number and divide it by 3, that's about 2,500 gallons per minute through each pump. So that's how I'm going to size my pumps. So this is going to be, well, I'm going to do a global edit. So I'm going to select those, edit, global junction edit for my pumps, select my pump data, sizing, 2,500. I'm only going to check the box for flow. That's the only thing I'm changing for those 3 pumps. So now we got 2,500, 2,500, 2,500, 2,000, 2,000, and 2,000. And we still have the original flow. 1,400 here, 1,300 here. We have 1,890 here, and 1755 here. So all of that is set up and ready to go. Now let's go back to our sizing panel. So my sizing objective, that's already done. My sizing assignments where I set up my common size groups, that's done. Candidate sets, that's done. But I do have a little bit more to do with my design requirements. So let's take a look at that. If I go back to my design requirements and I click on the pipes, you can see here that I still have just the 3 design requirements. I need to add 2 more for the higher flows of that second system on the right-hand side. So I'm going to take this row for the design requirement, I'm going to duplicate it. There we go. We give it a name. This is going to be called 1890 GPM HX A and B flow increase, or I'll call it 35% more. And I'm going to select that and change the value to 1890. I'm going to duplicate it one more time. 1755 GPM HX C and D flow, 35% more. And this is going to be 1755. So now you can see in the table below, we have 2 more design requirements, and we still have the same HX A and B pipes and HX C and D pipes. Well, this is where you need to expand those design requirements. So here, if I expand this, we now see the original system on the left and then the dependent design case on the right. All of our common size groups still have the 10 foot per second maximum velocity requirement. So that is not going to change. However, for my 1400 gallons per minute, that stays the same for these 3 pipes, but not for these pipes. These pipes are going to now use the higher flow design requirement. So I'm going to uncheck the box here and then check the box here. Those are the 2 boxes that I changed in order to get the design requirements to be proper for my dependent design case. So I've done that for the heat exchanger A pipes. Now I need to do it for my heat exchanger B pipes. Same sort of thing. I uncheck the box for the dependent value, the dependent pipes, and then I check the box for the higher flow for them. And then you would do the same thing for C and D. So now I'm going to uncheck the dependent design cases and set that to the higher flow at 1755. Same thing for D, 1755, and there we go. And now if I go back to my control valves tab here, this is where you can see that we still have our control valve requirements in play. Nothing needs to change here. That's all set up. Now, once I size my pipes for both systems and I find pump curves that will be able to meet those operating requirements, then we'll be able to check these additional boxes later. So that's all set up. If we go back to our dependent design cases panel, you can see here that this is just summarizing all of our design requirements. So this tells me for pipe 1, that's my original case, I have a 10 foot per second velocity requirement, and that's the same as pipe 1001, and this is my dependent design case. So this is just giving you a summary to show you what's going on for all of your design requirements. So that is all set up. Now I'm ready to rerun my sizing process. So I'm going to click on the sizing method. This time I'm going to click on suggest best method to see if there's a better method that will handle both systems. And it found one that was actually better. So now I'm going to choose that method and I'm going to go ahead and run my model. And it's going to go through the same process. It starts with my initial 16-inch diameter guess. It found that it's infeasible, and then it does the continuous sizing to see if it can find a better guess. And it did. That resulted in a piping weight of 328,000 pounds. Now it's doing the discrete sizing process. And that actually converges really quickly. Within 30 seconds, it's done. So let's take a look at our results here. So if we go to our output tab and we expand our general section to look at the cost report, this is coming in at 319,000 pounds. So if you remember the previous sizing process that we did, where we were only sizing for one system or one single operating scenario, the total piping weight was about 241,000 pounds. So we went from 241,000 pounds up to about 320,000 pounds so that we could accommodate higher flows. Higher flows mean we're going to need some larger pipe sizes. Well, what does the breakdown look like for that? If I collapse that and look at my sizing, here we can see that our pipe sizes are ranging from about 14 inches in diameter to 20 inches in diameter, and we have a few 16-inch diameter pipes here and there throughout the system. And if we look at our design requirements, we can see all of our design requirements are met, so that looks good. And this is where the visual report is really helpful, because we can see our pipe sizes for the entire system. So let me reset the label locations, and there we go. So we can see 14-inch for all of these, 14-inch. This is a 16-inch pipe and a 16-inch. We need a 20-inch pipe for the main header. That went from 18 inches in diameter up to 20 inches in diameter. However, here's something that's interesting, is the secondary header requires 14 inches in diameter there. Now, if you look at the expansion loop, we've got 14 inches and 14 inches as well. So that is how our pipes were sized. That's pretty amazing. I mean, it took the solver for this automated sizing process 30 seconds to be able to figure out my pipe sizes for me. But now this is where we're going to take things one step further. So this is where the other webinar took over, where I want to take the resulting pipe sizes for the system and I want to convert it to input for my workspace. So that's what I'm going to do next. So I'm going to go to my scenario manager. I'm going to create a new scenario called convert selected pipe sizes to input. It's real simple, everyone. You just go back to the output tab and you would click on the thumbtack right here. The thumbtack is where you can choose to transfer both calculated pipe sizes and calculated results, and click OK. So now if we go back to our workspace and we reload our scenario, we zoom in, bam, there it is. You can see that we have all of our pipe sizes set up all throughout the network, and we have it also set for the second system as well. That's beautiful. So we have all of our converted pipe sizes that were selected to input. Now we want to size our pumps. We need to find pump curves that will be able to accommodate both systems. So here's the next step is I'm going to go and create another scenario called get pump curve. You could do this in the same scenario if you wanted to. I just like to do things one step at a time in each scenario. So now I'm going to go to the sizing panel. This time, we don't have to size it again. So I'm going to create do not, or I'm going to click on do not size. That way it basically hides everything. This is just a straight fathom run. It's not doing any sizing, but it's still taking into account all of our design requirements. So now when I rerun this, the next thing I want to focus on is how are my pumps performing? So we can see here that we have two sets of pumps. We have 2,000 gallons per minute and 2,500 gallons per minute. So obviously when you size your pumps, you don't want to pick this option because then your pumps are going to be undersized for the 35% higher flow case. So we need to go with the higher flow pumps, and we need to use the operating point of 125 feet. So now I'm going to click on the pump with the spark on it. This is where you can go to find a pump vendor on the internet that will give you a pump that can meet this operating point. But we have to be careful. Pay attention to the basis pump from the model. Right now, this is selecting the lower flow pump. I don't want to do that. So I need to make sure I change this to the higher flow pump. So as you can see, 125 feet of head, 2,500 gallons per minute. So now we'll click on search. And if we click on open web browser, this is where you can go through the pump selection process where you can find a real pump curve from any of these pump vendors that will match your operating point. Now, I've already done that. I'm not going to walk you through that process. We have video tutorials on how to do it. So I'm going to go to step 2 because I already downloaded the file that I need for my pumps. And that's this pump right here. One second. Okay, so now I have all of this pump curve information. I need to apply this to the pumps in my model. So I'm going to click on apply pump data, and I'm going to choose which junctions I want to change, which is all of them. You could add this pump to your database on your computer. That way you can have this pump curve be available for other pumps and other models if you want. I'm not going to deal with that right now. I'm just going to click on apply, click OK, and click OK. And so now, if we go back to the workspace and zoom in, look at this. We now have our real pump curve, MPSH curve, and efficiency. So all of that data was brought in through the IQX file that I just imported. Super, super easy. This pump would be the same. All of the pumps are the same using that same pump curve. Same thing for this system. It's the same curve. Now, since I have pump curves in my model, I can actually go back and change the other two control valves in each system to the fixed flow values for my flow set point. 1,400 gallons per minute through that control valve, 1,300 gallons per minute through this one. And then when I scroll over here, this is going to be 1,890. And this one is going to be 1,755. Now, because I have real pump curves for my pumps, I'm going to add some additional pump output parameters to my results. So I'm going to do that with the output control window. Pumps, I'm going to add the MPSH required, MPSH ratio, percent of pump BEP, I'm going to add on the pump speed. I'm going to remove mass flow rate and pressure across the pumps. I'm going to rearrange these a little bit. Oh, I also want efficiency. So I want to know what the pump efficiency is going to be. So I've got efficiency, percent of the BEP, pump speed, and then MPSH. All right, so now I have those all set up. I can go back to my sizing panel and I can still check these boxes such that if any of those control valves have a lower than 10 psi pressure drop, it'll alert me. And that way it'll tell me if I have an infeasible design. So now let's go ahead and rerun our model with the pump curves. Let's take a look at our results. So we have, in reality, when you are able to control your flow through all of your heat exchangers with the flow control valves, you actually only need 1,800 gallons per minute through each pump in the lower flow system on the left and 2,400 gallons per minute on the higher flow system on the right. Now let's take a look at some of these other values. Our overall efficiency is 80% for the normal flow case, 83% for the high flow case. So the efficiency is doing really, really good. But we also care a lot more about the percentage of the BEP. So how close is the pump operating to its best efficiency point? Well, for the normal operating case, we're at about 76% of the BEP, which is actually really, really good. It's better than I'm sure what a lot of you see where things are operating at maybe 20% of the BEP. So I'm sure you would give anything to be able to get it to 76% any day. If we take a look at our valve summary, we can see here that we are getting exactly the flow rates that we need because that's what we specified. But take a look at the pressure drop across each control valve. For my high flow system, we're about 12 to 16 psi versus the normal operating case. Look at how much pressure drop it's taking out across each of those control valves. Almost 40% through each control valve. I'm a perfectionist, and so I want to see, is there a way that we can take this proximity of 75% of BEP and get that closer and improve it? Because if it keeps operating at 75% BEP, it's not bad. It's still within our preferred operating range, but let's try to see if our flow analysis tool can improve that. And this is where the goal seeking control module in AFT Fathom is extremely helpful. So this is a bonus for you all. And this is just amazing. So here's what I'm going to do is I'm going to create one more scenario, and I'm going to call it use GSC module to improve BEP proximity. Now, what I want you to pay attention to is not only the BEP proximity, I also want you to pay attention to the pressure drop across the control valves. 40 psi. Let's see if we can make this better. Now, when you use the GSC module, you can't use the ANS module at the same time. So I'm going to turn on GSC. You don't have to deselect ANS. You can just choose to ignore it. So I'm going to click OK, and I'm going to go to my analysis. And for automated sizing, I'm going to set this to not used. So now I'm not using automated sizing, but I do want to use GSC. So I'm using GSC, I'm not using ANS. And so now I'm going to go to my goal seeking control manager and I'm going to set up a variable. So what am I going to vary? I'm going to try and vary the pump speed for each of these pumps in the normal flow case. I'm going to try and, because all of those are operating at 100% speed. I'm going to see if I can change the pump speed and maybe drop it down a little bit to allow those pumps to operate closer to the BEP. And you'll also see how the control valves respond accordingly. So I'm going to add on 2 more variables. This is going to be the second pump, pump B, and pump C. Now, I don't want these pumps to have 3 individual speeds. I want them all to be the same. So I'm going to take the second 2 pumps and I'm going to link them together to the first pump. That way they have the same pump speed. There we go. Now my goal is going to be for a pump. My goal is to try and get my proximity to the best efficiency. Let's go from 9. Let's see if we can get 90%. So I'm going to do 90% of the BEP, and I want this for all 3 of those pumps. Now, we have 3 variables which were basically collapsed down to 1 due to the linking, and then I have 3 goals. So it's basically 1 variable effectively to 3 goals. Usually you want to make sure that you have the same number of variables as the same number of goals for a unique solution, but this is still going to be fine and it's going to be able to work for us. So that's what this message is telling you. It's fine, we're just going to do it. And so now, if I zoom in, we can see that we've got a variable and a goal for each of those pumps. So now let's go ahead and run the model. All right. Now, the goal seeking control module can be used in a lot of different ways. And I believe that the runtime for this scenario takes just a couple of quick minutes. So while that's running, what it's doing here is it's trying to get closer and closer to my goals that I specified by changing the pump speed for that system. As an aside, one thing I want to talk about is the GSC module. If you go to a products menu and then back to AFT Fathom, scroll down, and this is where you can learn more information about what the goal seeking control module does. So if I access goal seeking control, you'll be able to see some ideas of how you can use GSC to increase your productivity and avoid manual iteration and many, many other things. So both the GSC and ANS modules are extremely useful. Make sure that you check that out. All right, how's our iteration process going? It's doing a lot better. When GSC is running, it's trying to get your best value down to 0. And so it's doing pretty good. It should converge here in the next 30 seconds or so. So just hang tight with me. The reason why it's taking just a little bit longer is because of the non-linearity due to pump curves. Before, when we were doing all of the ANS stuff, it was fixed flow pumps. It was a single value, and it was a lot easier to be able to get convergence on that. Now that we have pump curves entered in, we have a lot more non-linearity in our model, and that's why it's going to take a little bit more time to get convergence. And as you can see, what it's also doing for just about each iteration, it's adding relaxation, so that way it takes smaller steps, one iteration to the next, as it's trying to bounce around on the curves with the Newton-Raphson method as well. Imagine trying to do this by hand. It would take a lot more time and be a lot more difficult. There we go. All right, so our calculations are complete. Let's take a look at the output and to our pump summary. Okay, so what we were able to see here is that we did achieve 90% of our BEP. Excellent. That's great news. And the way that we got there is by changing the pump speed down to about 84%. So if you change your pump speed down to 84%, you're going to be able to get that pump uh, a lot closer to its best efficiency point, which is definitely something that you always want to try and do. Our flow rates are still basically the same, and so we did a really good job there. If you take a look at the variables, you can see 84% speed for all three pumps, and we're all hitting 90% of the BEP. But let's go back to that control valve summary. So we look at our control valve summary. Look at this. For these four control valves, it dropped from 40 psi across each control valve down to about 18 to 19 psi. That is huge. That is amazing. So your pumps are going to operate a lot more reliably because they're operating much closer to their best efficiency point. You do achieve a slightly higher efficiency for each of the pumps. You went from about 80% up to about 83% for this scenario. So that's pretty good. But when you take a look at these control valves, they're not having to add so much more pressure drop to maintain their set points. And that's a huge deal. That's also going to have a, excuse me, I keep hiccuping. That's going to have a major improvement in your energy cost as well. So if you really wanted to take this further, what you could do is you could do another scenario where you go back to using ANS, and instead of sizing your pipes, the option that you would choose is you would go here and you would say ignore GSC and then use ANS, and you say calculate weight, do not size. And actually, you could do a monetary cost, but you're just doing a cost calculation. And so here, we're not trying to minimize, we're just trying to do cost calculation. So how much does it cost in 5 years? Give it a energy cost value, 11 cents per kilowatt hour, whatever it is, and then run your cost calculation, and you'll be able to determine how much energy costs you're going to be saving by going from running your pumps at 100% speed down to 84% speed. And that way your control valves are not having to take out huge amounts of pressure. It allows everything to work so much better. So this is a great example, and we covered a lot of stuff. So just a quick summary. We started off with our initial system where we were talking about how you do a automated sizing process for just one operating case. We set up all of our parameters for our ANS module, common size groups, candidate sets, things like that, design requirements, and we sized the pipes. Then we took it one step further where we looked at a dependent design case, and we created this system here on the right, which is an identical system of the left, but its intention is to model a different operating case at higher flow capacity. So with that, we needed to resize all of the pipes in order to meet both operating cases. Once we were able to size our pipes for both operating cases, we then converted the resulting pipe sizes to input, and then we were able to find a pump curve that matched the operating point that we needed. Once we got the pump curve, we saw that it was within excellent BEP proximity for the high flow case, but maybe this is only 30 to 40% of your operating time. The majority of the time it operates at these flow rate values. Well, this ensures that your pumps are not uh, undersized. But they are oversized for this system in that case. So then we used the goal seek and control module to tweak the pump speed for the normal flow cases in order to get those three pumps to operate closer to their BEP, and that also led to a dramatic reduction in the pressure drop across these control valves. Better pump operation, better reliability, more cost savings for maintenance and energy costs, and there you go. Well, thank you all very much for your time today. I appreciate you listening in. If you want to try out the GSC and ANS modules or any of the Fathom modules, please let us know and we'll be happy to accommodate that for you. Take care, everyone, and have a wonderful rest of your week.